Welcome to the data metaphor space. Today, our topic is how to understand the average and worst case performance of the quicksort algorithm. First of all, I would like to invite today's two guests, Mr. Wisdom Big Eyes and Miss Alice, who likes to walk catwalks. Let the two guests say hello to the audience.
Quicksort is one of the fastest sorting algorithms, and it is also one of the best cases of using the idea of divide and conquer. However, how big is the quicksort? Is its performance stable? Let's continue below. Just like you have a party, suppose the x-axis is the number of people who come, and the y-axis is the time needed to make the cake. Let's first understand the symbols that represent performance. O(1) is constant time. Given an input of size n, the approximate algorithm only needs one step to complete the task. O(n) is linear time. Given an input of size n, the steps required by the algorithm to complete the task are directly related to n, one-to-one relationship. Log n is logarithmic time. Given an input of size n, each time the algorithm executes a step, the number of steps it needs to complete the task will be reduced by a certain factor. N squared is the quadratic time. Given an input of size n, the steps required to complete the task are the square of n. C(n) is exponential time. Given an input of size n, the steps required to complete the task are a constant n, very large number. The performance of quicksort is highly dependent on the benchmark value you choose. Suppose you always use the first element as the base value, and the array to be processed is ordered. Since the quicksort algorithm does not check whether the input array is in order, it still tries to sort it.
Let's continue. Today, our topic is how to understand the average and worst case performance of the quicksort algorithm.
Please pay attention. The array is not divided into two halves. On the contrary, one of the sub-arrays is always empty, which results in a very long call stack. Now suppose you always use the middle element as the base value. In this case, the call stack is as follows. In this way, the call stack is much shorter, because you split the array in half every time, so many recursive calls are not needed. You reach the baseline condition very quickly, so the call stack is much shorter. The first example shows the worst case, and the second example shows the best case. In the worst case, the stack length is O(n), and in the best case, the stack length is O(lone). Now let's look at the first layer of the stack. You use one element as the base value and divide the other elements into two sub-arrays. This involves all 8 elements in the array, so the operation time is O(n). In the first layer of the call stack, all 8 elements are involved, but in fact, O(n) elements are involved in each layer of the call stack. Even if the array is divided in different ways, O(n) elements will be involved each time. Therefore, the time required to complete each layer is O(n). In this example, The number of layers is O log n. In technical terms, the height of the call stack is O log n, and the time required for each layer is O n. Therefore, the time required for the entire algorithm is O n asterisk O log n equals O n log n. This is the best case. In the worst case, there are O n layers, so the running time of the algorithm is O n asterisk O n equals O n2. You may find it strange that for quicksort, the best case is also the average case. As long as you randomly select an array element as the base value each time, the average running time of the quicksort will be O n log n.
Readers can think about how long each of the following three operations will take. 1. Print the value of each element in the array. 2. Multiply the value of each element in the array by 2. 3. Only multiply the value of the first element in the array by 2. Thank you two guests for the discussion and sharing today. Let's see you next time.